Now let's talk a little bit about linear modeling and what a linear model really is. So modeling, to start off with in a very general sense, is a general, often mathematical statement of a hypothesis. Right? It's some general statement about how something in the world is working. There are three different types of models, broadly speaking. The first of these is a theoretical or a mathematical model. These are often equations or graphical representations of equations that are abstract, right? They're theoretical. There's no real-world data necessarily. Few parameters. They're trying to make a general statement about how a process works in the universe. A second type of model is a simulation model or a computational model. In these models, right, you tend to have either a mathematical equation that you are exploring iteratively, that you are repeating potentially a large number of times and seeing how things vary over the course of those different iterations. This could also be not necessarily, strictly speaking, a mathematical equation, but some sort of decision, perhaps, that an agent or an individual that you have programmed is making. You could program a bunch of individuals to have certain behaviors based on certain kind of mathematical processes and make those agents or individuals interact with each other and then explore over the course of numerous iterations or kind of repeated interactions what happens in this model. An agent-based model, which are known as individual-based models as well, would be an example of this sort of simulation or computational model. These really require kind of computer modeling. They're computerized, they're computational, they require a lot of processing power in some cases to run because they can get a little bit complex. But finally, the third type of model that we're really going to be talking about is a statistical model or an empirical model. These types of models are expressions of effects or relationships, the strength or the kind of direction of an effect or a relationship based on real data. It requires data from the real world, unlike the previous two types of models. And that's really going to be the focus of this class. Now, I would be remiss if I didn't include this quote from the statistician George Box in this discussion of modeling, because it's important to understand what exactly a model is and what it's doing and what it's capable of and not. And so George Box famously said, "All models are wrong, but some are useful." And this kind of perfectly captures what the point and limitations of modeling are. All models are wrong, right? That first part is a reference to the fact that models are deliberate oversimplifications of reality, right? They are actually, by definition, wrong. They're inherently wrong. They're meant to be wrong because if we were to try to replicate the universe in a mathematical equation or in a computational simulation, right? It just couldn't be done. Things are too complex, too complicated. There's too many variables and moving pieces and parameters. And so what we do as modelers is distill things down, simplify things down to kind of the key pieces, and then explore those, right? And because we're doing this simplification, right, our models are, of course, wrong, right? The only way they would be right is if they were perfect reflections of what's actually going on in the real world. And so saying that a model is wrong is really kind of meaningless because models are all wrong, but some models are useful, right? And that means that through this kind of careful oversimplification, this careful reductionism, we can actually gain some insight into what's going on in the world. Right? By focusing our attention on specific moving pieces of the real world in a modeled format, it is actually possible to better understand how things are manifesting in the universe around us. Right? I had a professor who used to describe models as little toy worlds that we build, right? And then we play with them, and hopefully they can tell us something about the real world. But these little toy worlds that we build Describing them as wrong or incorrect is just a silly thing to do. Of course it's wrong, but the question is not whether it's wrong or right, but whether it's wrong in a useful way. All right? If your model is able to be used to say something insightful or meaningful, then it's certainly a good model. In this class, we're focused on statistical models, as I said, and most commonly this takes the form of regression. Now, regression is a statistical technique used to determine the effects of some variables on other variables. Right? It can quantify the strength, the nature, the direction of relationships between variables, the effect that one has on the other. The way that it does this is it kind of describes two different types of variables. First, you've got your predictor variable. Some of you might have encountered the term independent variable. It's the same thing. This is generally the variable that goes on the x-axis. And this is the variable that we use to then predict our other variable, which is called the response variable. Again, you might have also heard this as the dependent variable because it depends on the independent variable. I prefer the terms predictor and response, right? Your response variable, typically on the y-axis, is whatever it is that you're trying to better understand, right? It's something that you've observed in the world, and you're using your predictor variable to kind of assess the relationship between the two, the effect that the predictor variable has on the response variable. And so these two terms, predictor and response, are going to come up time and again. So kind of understand what the predictor is, what the response is. Predictor generally goes on the x-axis, and you use it to predict the response variable on the y-axis. Now, the way that most people have historically and kind of to this day teach statistics is kind of captured in this little flowchart here. We've got this sort of schematic where it starts off with whatever type of data you're dealing with. Are your data continuous or are they discrete? If your data are continuous, then are you exploring relationships or differences? Do you have a true independent variable, yes or no? And you work through this flowchart until you result in a statistical test, like regression analysis, or Pearson's R correlation, or ANOVA, something like that. Many of you have taken statistics, and if you've thought about statistics in any way, it's probably in the form of this sort of chart that, depending on the different question you have and the type of data you're dealing with, what test should you use? Should it be an ANOVA, a t-test, a Kruskal-Wallis test, whatever? I will not be teaching this course like this. I am definitely in agreement with kind of a growing trend in statistics education that we should really just be focusing on what a linear model is and ignore a lot of the rest of this. And the reason is because every single statistical test that you see on this chart, from a chi-square test to a Pearson's correlation, a Spearman's correlation, Kruskal-Wallis, ANOVA, Mann-Whitney, t-test, all of it, they're all linear models. Everything on this chart is just a specific type of linear model. And so we don't actually need to unpack all of the different kind of particularities of each specific little test, as long as we understand what a linear model is and what it can do. If you don't believe me on this, I've got a chart here in this slideshow that you can pull up and inspect this, because here it is, each of these different common tests, a t-test or a Spearman correlation or whatever, and how you would program it in R and kind of the way that it breaks out. And this demonstrates to you that actually every single one of these is just a linear model. And so for that reason, I'm going to be teaching you linear modeling. Right? I'll make a note whenever we encounter something like, oh, by the way, this is a t-test. But for our purposes, really, just focus on understanding what a linear model is and how to apply it to your data. Now, a linear model has two key parts. The first of these is called the deterministic part of the model. The deterministic part of a linear model is a mathematical statement of a process, some process out in the universe, and we are kind of quantifying it mathematically, describing it mathematically. The deterministic part of a linear model is, for example, this red line here on this plot, right? And this red line is shown in this equation here. I know this is an applied statistics class for archaeologists and anthropologists. I know a lot of archaeologists and anthropologists are a little bit math phobic. Believe me, I understand. I'm actually the same way, believe it or not. And I wouldn't be showing you this equation if I didn't think it was important, and it's actually not all that difficult to understand. What this equation is doing, as an expression of the deterministic part of a linear model, is trying to calculate this mu sub I value. This mu sub I is the red line, right? Mu stands for mean. The mean is the red line here. Sub I, the little I there, is referring to different points along the x-axis, different points along this red line. And so when we're calculating the mean, this red line, what we need to do is account really for a couple different coefficients, a couple different parameters. The first of these is called beta naught, or beta 0. This is commonly known as the intercept, and this is the value of mu when our x is equal to 0. Right? Whatever our predictor variable is, and we've got our response variable on the y-axis, the mu is the mean of the response variable. Right? Whenever x, our predictor variable, is equal to 0, beta naught is the value of mu. Right? What we then do is take that kind of baseline estimate of mu whenever there is nothing going on. There's no effect, there's no relationship. When x is 0, right? We take that beta naught value and we add it to another beta coefficient, beta 1. Right? Beta 1 is sometimes called the slope. The slope, for those who don't recall from grade school math classes, is the rise over the run, so to speak. You go up x number of units on the y-axis, x number of units across on the x-axis, divide those values, and that's your slope, right? If you go up 1 and over 1, that's a slope of 1. You go up 5 and over 5, that's a slope of 5. You go up 1 and over 5, your slope is 1 over 5 for 0.2. Right? This is kind of easy to understand if you think of it as the effect of the predictor variable. Right? Beta naught is simply mu at a value of 0 for the predictor. But beta 1, what we do is multiply that times our value of x and add it to the intercept. Right? So as a little just like quick illustration here, again, we're going to get into this later, but if we're trying to predict an x value, or rather trying to predict the mu value, this red line, for an x value of 43 right here, we take beta naught, the intercept, and we add it to beta 1 times 43 right there. And that will give us a mu value that is around 300, that red line right there. Right? If this isn't making sense yet, don't worry. We're going to actually work through real examples of this equation later on. But I just want you to understand that this equation here is the deterministic part of a linear model. It's how you calculate the red line, the predicted mean value. And if you've got more x variables, more predictor variables, you can add more terms. That's what this extra bit here is noting. But don't worry about that for now. Most examples that we're going to use are just going to have beta naught and beta 1. Now, the second part of a linear model is called the stochastic part, where the deterministic part was a mathematical statement of a process. Right? The stochastic part of the model is a probabilistic statement about the data that arise from that process. Right? I told you that the red line is mu. The red line is our deterministic model. The actual data that we observe, these black circles, right, those arise not from the deterministic part, but from the stochastic part. Right? So if you want to actually figure out a value of y, right, this data point here, for example, is not on the red line. Right? And so if you're looking at that data point and trying to figure it out, the red line itself isn't going to actually tell you what's going on. You need another part. That's the stochastic part. Y is distributed as some sort of probability distribution around mu, around that mean value. So this mu value from the deterministic part, the red line, gets plugged in to a probability distribution. It helps define a probability distribution. In this case, because we're dealing with just a basic linear model, it's a normal distribution. And I've plotted all these different normal distributions along that red line, along that model fit. The actual data that we've observed, these gray or black circles, those are y, and those are distributed as a normal distribution based on the mean, that red line. Right? That's where the data are actually coming from. Right? The deterministic part of the model tells us the general process, and the stochastic part tells us how we actually get the data from that process. And the reason it's just stochastic is because there's a lot of randomness in the world, and we can't perfectly capture everything with our deterministic mathematical equation. We recognize that there's uncertainty out there, there's other stuff going on. That's stochastic, it's random. And so capturing that simply as a probability distribution is a simple way to approximate what's going on in the real world without measuring every variable, because we just couldn't do that. And so these are the two parts, right? Deterministic part and a stochastic part. Again, if this isn't clear, we're going to talk a lot more about this, so don't worry at this point. Now, this linear model, the deterministic part, for those of you who have good memories of grade school math, algebra, or statistics classes, might recognize it in a slightly different form. When I was in school, we learned y equals mx plus b. Some of you might have learned y equals b plus ax or something like that. But this is the same thing as the linear model that I just showed you, right? Back when you're in high school or middle school or whatever, with your TI-83 calculators, right, running these equations, the intercept, right, beta naught, or beta 0, that's b in this equation, right? That's the value of y in this case at x equals 0. Beta sub n, or in this case beta 1, right, that's your slope, that's m. That's what you multiply by the x value that you're trying to understand and then add to the intercept to predict the y, right? X is your predictor variable, and mu sub I in our case is the same as y in this y equals mx plus b equation. It's the response variable. It's what we're trying to predict. We use x to predict y, right, by multiplying x times the slope, adding it to the intercept, and that's how we get y. Right? Just as in our model, we're doing the same thing. We're just using slightly different terms, more general terms. So again, if you didn't learn y equals mx plus b, this slide might not mean much to you. But if you did, hopefully this is making some connections, that this isn't actually new information for you. You might have actually learned this before. Now, linear models make several assumptions about data. Right? There are 6 that I really want to focus on, and I'm going to list them in order of their importance. The first assumption of a linear model is that the model actually makes real-world sense, that the model predicts values that are realistic. Right? For example, let's look at this plot here. On the y-axis, let's say that this is a measurement. Maybe it's the length of a certain bone, right? The length of that bone is continuous, as we talked about in our probability distribution lecture, but it's bounded by 0, right? You can't have a bone that is negative 10 centimeters long. That doesn't make real-world sense. So if you're using a linear model, right, and as we've said, a linear model at kind of its base level assumes that your data are normally distributed and can take any value from positive infinity to negative infinity. That linear model, which is shown here by the red line, will just keep going in either direction towards infinity. And so if you're modeling a measurement, for example, your model is going to predict negative values at some point. And that probably doesn't make real-world sense. Right? So depending on how your data look, you might not want to use a linear model. You might be violating the assumption of a linear model. It can cause problems for you. Sometimes it might not, but sometimes it might. And that's something to be aware of. And so this is the most important assumption. If your model doesn't make real-world sense, right, there's a problem. Your model should be making real-world sense. That's just kind of the baseline level. And that kind of undergirds a lot of these other assumptions as well. Now, the second assumption is the assumption of additivity. This one's a little bit more complex than we're going to get into in this course, but the gist of it is that when you've got these different beta coefficients, a linear model adds them together, right? It's beta naught plus beta 1 plus beta 2 plus beta 3 and so on. It's not beta naught times beta 1. That would not be additive, right? That's multiplicative. That's something different. That's not a linear model. So the models that we're dealing with are going to be additive. Again, we're not really going to get much into this assumption, but it's something to be aware of. And it is important that if your model is not a relationship that is additive, that the coefficients can be added together, you're not dealing with a linear model. You violated the assumption of a linear model. The third key assumption of a linear model is linearity, right? If you've got y data that are distributed like this curve here in this plot, and you fit a linear model to it, that linear model will be this red line, right? And obviously this is an absurd model to try to fit to these data. It's not capturing hardly anything about what's going on in these data. And so when you're dealing with something that's not linear, right, this nice curve here, that would violate the assumptions of a linear model. You couldn't really use a basic linear model to model this, at least not well. Now, the next three assumptions actually all have to do with this concept of a residual. A residual, which can also be known as the errors in the model, residual is kind of that distance between your real data point and the predicted value for that data point, your model fit, that mu sub I. So the deterministic part is generating that mu sub I, that mean value, and the stochastic part of the model, right, is determining kind of where your data actually fall out. That is what has to do with the residuals. So this distance between your point and the line is the residual. You want that to have certain characteristics in the case of a linear model. The first of these is that you want those errors, those residuals, to be independent of each other. Right? If this black line at 0 is our model fit, we don't want our residuals, our data points, to look like this. Right? These data points are correlated to each other. Data points that are closer to each other along the x-axis are more similar than ones that are further from each other. And we don't want that to be the case. We want all of these points to kind of just be randomly scattered around that deterministic part of the model, around that best fit line, that regression line. We don't want this sort of patterning, which is showing that these errors, these residuals, might not be independent of each other. They might be correlated to each other, and that can cause problems. Additionally, we also want those residuals to be distributed evenly across all of the values of the x-axis, across the entire length of our model fit. If, for example, you've got a pattern like this, these data points, in this case, these residuals, are increasing in variance, right? The variability in these residuals is increasing as you move from a value of 0 on the x-axis up to a value of 100. There's a lot more variation in the residuals up here. This is called heteroskedasticity. Heteroskedasticity. This is bad. This violates the assumption, this fifth assumption of a linear model. What we want is homoskedasticity. We want the variance in these residuals to be consistent along the entire range of the x-axis, along the entire range of our predictor variable. If we've got heteroskedasticity like this, we're violating the assumption of a linear model. And finally, the sixth assumption, and perhaps the least important, but still important nonetheless, is that our model should have normally distributed errors. Right? So not only should those errors be uncorrelated to each other and independent, not only should they be evenly distributed consistently along the predictor variable, but they should be normally distributed. Now in this plot here, what I'm showing you are errors that look like they might be independent. They look like they might even be homoskedastic. They look like they're kind of evenly distributed, but they're not normally distributed. Right? Remember that a normal distribution is continuous and unbounded. The data here are count data. You've got 0, 1, 2, 3, 4, 5, and 6, with nothing in between. That's not continuous. So these residuals would not end up being normally distributed. Right? Additionally, normally distributed would require them to be negative too, and if these are count data, right, that becomes a little bit problematic. So because the data here are not coming from a Gaussian process, they're coming from actually a Poisson process, if you recall that from our lecture on probability distributions. They're not normally distributed errors, most likely. And so this would violate potentially the assumption of a linear model as well. Now, if you've been thinking about these 6 assumptions, hopefully you realize that a lot of data out there in the real world violates at least one, if not more, of these assumptions of a linear model. In this course, we're going to learn a little bit how to deal with some of these violations. There are different ways that you can accommodate violations of these assumptions, and here we're going to cover violations of assumptions 1, 5, and 6, whether the model makes sense, if the residuals are homoscedastic or not, and whether their residuals are normally distributed. To a lesser extent, we're also going to talk about linearity and some ways that we can accommodate that potentially as well. What we're not going to talk about are violations of assumptions 2 and 4, and in a certain senses 3 as well. If you're dealing with a model that's not additive and doesn't have independent errors, that gets a little bit more complex. That's going to be outside the scope of what we can cover in this course. But hopefully by the end of this course, you'll be able to understand what's going on with linear modeling enough to figure out what you need to do in those cases if your data end up being problematic in those ways. And finally, when you're interpreting the results of a linear model, we're going to get into the practicality of this a little bit later on. But to start off with, as a refresher, p-values, right? A p-value, as we discussed in a previous lecture, is the probability of your data, or more extreme data, given the null hypothesis is true, and given that you've repeated your experiment or observation an infinite number of times. But so the probability of your data, assuming the null hypothesis is true, right? In the case of a linear model, the null hypothesis is that there is no effect of x on y, that there is no effect of the predictor on the response variable. There's no relationship between those two. If your p-value is small and significant, that suggests that your data are quite unlikely to arise if this null hypothesis were true. And so you might be able to reject that null hypothesis. We'll talk more about how you go about this process of understanding p-values in linear models a little bit later. But I also wanted to introduce here the concept of an r-squared value, which again we're also going to talk more about in the future. An r-squared value is a measure of goodness of fit. It's the strength of the effect or the relationship between your predictor and the response. So a p-value tells you whether your data are likely or not if the null hypothesis is true. An r-squared value doesn't tell you whether your data are likely or not. It tells you kind of the strength of that relationship, how much extra variation there is being added in by that stochastic part of the model, so to speak. How far we're getting from that deterministic part of the model, that really kind of simple, mechanistic, mathematical explanation of the process. If that were capturing almost everything going on in the real world, then our r-squared value would be great. There wouldn't be much spread in our data points around that line, or perhaps none at all, even if it was perfect. But if there's a lot of stochasticity involved in this, if that, for example, normal distribution has a pretty wide standard deviation, there can be a lot of variation around that deterministic part of the model, around that model fit. And then our r-squared value would be lower, right? R-squared values range from 0 to 1. Generally speaking, a value of less than 0.3, that's a weak relationship, or perhaps no relationship at all. If you get between 0.3 and 0.5, you can call that a weak relationship. 0.5 to 0.7 is moderately strong, and anything above 0.7 is a strong relationship. It means that your model is able to explain a lot of what's going on. Now, the formal definition of an r-squared value is the proportion of variance in your response variable, in y, that is explained by your model that includes your predictor variable, or x. All right? It's the proportion of variance in y that's explained by x. All right? So if you've got an r-squared value of 0.5, that means half the variance in y can be explained by x. That's not terrible. It's not great. If you've got something like 0.8 or 0.9, that means that 80 or 90% of the variance in y can be explained by x. That's pretty good. That means your model's capable of explaining a lot of what's going on in the data that you've observed. Right? But again, this is not the same as a p-value. This is saying nothing about the probability of your data, right? Or whether a null hypothesis is true or not. That's not what an r-squared value is about. It's just the proportion of variance that you're able to explain. We're going to talk more about r-squared values and p-values and some ways that we calculate both of those in different ways in some coming tutorials.